So today we're going to start the topic of supernova. Okay. You guys have these. Right. We know nebula, going protostar, begin on the main sequence using hydrogen and helium. This is true for all of them. When that hydrogen runs out, then we'll begin fusing helium and things like carbon, etc., etc. Beyond that, if you're a smaller star, I'm going to say something 8 times the size of our sun or smaller, then as you run out of material in your core that you can fuse, and so you stop having that outward pressure, gravity is going to collapse that star down into a white dwarf. The outer layer, the core of it, the outer layers are just going to drift off into a planetary nebula. That's what happens on the lower section here. On the upper section, it's a whole different story, right? We go from just being a massive star to being a red supergiant, and then you see the next thing is this supernova, okay? And so we talked a little bit about this idea of a supernova, of white dwarf and neutron stars last time. It's kind of where we're going to pick up now, okay? So it's all about size of the core, remnant core. Okay, if the size of the core is 1.5 solar mass units or more. Let's do this. If core is less than about 1.5 suns, then all you're going to get is a white dwarf and planetary nebula. If that core is 1.5 or greater, then you're going to get a supernova. Only question from there is, how much is left after the supernova? If there's enough matter left after the supernova, then, well, if there's enough left after the supernova, you'll go black hole. If there's less, you'll go neutron star. From supernova, we can go 2 locations. We can either go neutron star, or we can go black hole. But the transition from being a red supergiant to becoming either a neutron star or a black hole is a supernova event, which is where it's going to explode, right? So you think about one of these large stars, they're huge, absolutely huge. They're 8 to 10 times the size of our sun, right? Or more. Okay. When they are done with their main sequence, they're going to become supergiants. When they're done being a supergiant, there's still this core that's in here that is going to be huge. The core itself is going to have 1.5 or more times the size of the mass, the material of our sun. When there's no more pressure pushing out and there's only gravity pushing in, it will explode rapidly. It will fuse all kinds of larger elements, and then It's either going to become a neutron star, which we looked at a little bit last time, or it's going to become a black hole. But either way, what happens right here, when we're completely out of pressure, moving out, and this thing crashes so hard due to gravity, there's so much energy, so much power in that as it heats up, it explodes in one final, and it just sends all of this material out into space, okay? And you're left with a supernova remnant. It's going to be huge. It's going to cover just light years of space. It would be great if I knew where to put the cap to this thing. Probably in my pocket. There it is. Now, well, yeah, 8 to 10 times mass for sun. Okay. I want to show you a video. We'll probably stop. I'll ask you some questions. We'll review some things. When the video's over, and we're done with that, we go home.
What?
Alright, here we go.
I hope.
Got it.
In my mind.
Okay, just follow here.
Yeah, like, you?
Alright, y'all, here we go.
That's my group. I ain't seen that.
This next song that I'm going to play.
Extension of the word nova, which means new in Latin. A nova is a type of stellar event in which a new luminous object is created by binary stars, which fades away slowly after. A supernova follows a similar pattern in luminosity. A brief, bright peak followed by an extended dimming. The difference, however, is that a supernova is caused by a catastrophic explosion, one which destroys the object initiating it, rather than creating one. Supernovae occur either when a very massive star has reached the end of its energy generating cycle, or when the interactions of binary stars lead to unmitigated thermonuclear reactions. Either way, an apocalyptic explosion ensues in which an incredible amount of radiation is released, from radio waves to X-rays to destructive gamma rays, which pulverize the star's surroundings, wreaking havoc on planetary systems within about 50 light years of the epicenter. The good news is that lone dwarf stars like the Sun are not massive enough to explode in this way. Only stars with a mass about 8 times that of the Sun will be able to initiate the extreme gravitational and nuclear reactions needed. When a massive star can no longer keep itself held up, its layers collapse at tremendous speeds, resulting in an explosion billions of times more luminous than the Sun, lighting up its surrounding galaxy and shining for millions of light years across space. Considerable amounts of the dying star's material, equivalent to at least 5 times the mass of our Sun, are ejected outwards with unshakable force, creating a shockwave that carries material for light years into its surrounding interstellar space, inevitably leaving behind a bright and beautiful nebula. This material floods the interstellar medium gas clouds between stars with heavy elements released from the departed star's core, creating a richer, more fertile environment for new generations of stars than the one that the star in question was born into. Novae and supernovae were known long before we understood their underlying causes. There have been many cases throughout history of naked-eye supernovae which caught the attention of ancient observers. Perhaps the most significant came in the year 1006, when an awesome supernova, dubbed SN 1006, dazzled in the sky for a few weeks. At its peak, it would have been 100 times brighter than the planet Venus in the sky, strong enough to shine during the day and cast shadows at night. Thought to be the brightest supernova from Earth in recorded history, it was greeted with astonishment and anxiety alike by observers all over the Northern Hemisphere. The Japanese described it as white and blue in appearance, while the Chinese referred to it as a guest star. Astronomers have since scoured historical records to ascertain the location of this supernova, tracing it to somewhere within the constellation of Lupus. And in that region, we do indeed find a nebulous remnant which appears to be around 1,000 years old. Another significant supernova came around half a century later, when a massive star in the horn of the constellation Taurus exploded. It wasn't nearly as bright as SN 1006, being estimated to be only as bright as the planet Jupiter in the night sky. But unlike our neighbouring planet, the supernova remained visible during the day, attracting the attention of Chinese, Korean, and possibly even Central American observers. The remnants of that explosion are well known to us today as one of the most studied objects in our local neighbourhood of space, the Crab Nebula, a glowing cloud of supernova ejecta, lying around 6,000 light-years from the Earth. Initially, it was thought that these events were the birthing of new stars, hence the name meaning new in Latin. But by the 1930s, it was understood that these transient phenomena were the result of stellar explosions. The class supernova was coined in lectures and papers to refer to a new class of nova in which the star was destroyed in the process. Our understanding of these cosmic catastrophes has only improved from there. But there is a problem. Supernovae are quite rare, on human timescales at least. It is estimated that they should occur between every 50 to 100 years within our galaxy. But sadly, we haven't managed to catch one occurring within the Milky Way galaxy since the invention of the telescope. Nevertheless, we have managed to see a great many supernovae occurring in other galaxies. However, there is no meaningful way to predict where one might occur next, and their vast cosmic distances make their intrinsic properties difficult to constrain. However, all of this changed in 1987, when a supernova occurred barely a stone's throw away from the Milky Way galaxy, on a cosmic scale anyway. The Large Magellanic Cloud is a torrid, gaseous dwarf galaxy, lying a mere 160,000 light-years from the Earth, in a fairly unobstructed position of the sky. As such, many of its hundreds of thousands of massive supergiant stars are a great deal more visible than some of those in our own galaxy. And so, when a supernova illuminated the cloud in the late 80s, astronomers were able to get their closest and best look at the phenomenon, deducing a great deal of new information about the properties of these explosions. What's more is that, thanks to previous efforts to study the satellite galaxy, we knew what kind of star SN 1987A was before it went supernova, specifically a luminous blue supergiant. This helped us to combine our theories with actual observations, allowing for a much deeper understanding of both the prerequisites and aftermath of these explosions. And SN 1987A remains, to this day, the last supernova that was visible from Earth with the unaided eye. Finding and classifying supernovae used to be difficult and tedious. We relied almost entirely on amateur astronomers and volunteers to sift through contrasting photographs of space, looking for any new luminous sources that may constitute a supernova. Thankfully, automated computer systems and improved surveying technologies have since removed a lot of the legwork. We can now survey millions of stars and billions of galaxies. Notwithstanding the fact that we haven't seen a supernova occurring within the Milky Way for over 4 centuries, we are now discovering hundreds of new extragalactic supernovae every year, some which lie deep into the observable universe. At a first glance, these explosions all seem fairly similar, but if we take spectroscopic measurements of the explosion while it's happening, the presence of certain elements can be determined. That's how we classify supernovae, based on their prevalence of hydrogen, the lightest and most common element in the universe. Type 1 supernovae do not show any hydrogen in their spectrums, whereas Type 2 supernovae do show hydrogen. We can also break these two classes down further, based on the behaviour of the supernova's light curve or by the presence of certain heavy elements. This system of classification was introduced in the 1940s by physicists Fritz Zwicky and Rudolf Minkowski. Back then, there was nothing to work with inside our galaxy. The only supernovae they could classify were ultra-bright extragalactic supernovae, and thus our first type, Type 1s, are actually the more luminous and rare type, whereas Type 2s are your classic dwarf star collapsing under the weight of its own gravity. Therefore, we will begin with Type 2 supernovae, explosions caused by stars at the end of their lives, which show hydrogen in their spectra. As we mentioned, only stars more than 8 times the mass of the Sun are heavy enough to explode. Below this threshold, a star will not be able to compress its core to the level required to initiate a supernova. Stars like the Sun fuse their core hydrogen fuel they are born with into helium, and the helium into carbon, but they won't proceed much further beyond that. More massive stars, however, continue to work their way up the fusion chain, gradually fusing heavier elements at ever-increasing temperatures. Each time an elemental fuel source is exhausted, the star briefly contracts, making its nuclear furnace hotter and denser. Eventually, the carbon supply in the core is fused into oxygen, neon, and magnesium. Once carbon is exhausted, the process repeats and the star contracts again, this time fusing the oxygen and other elements into heavier elements still, like silicon, sulfur, calcium, and argon. Then, at an even greater level of compression, these elements can be fused to form iron, and this is where the energy-generating phase of the star's cycle ends. Up until now, the fusion of elements within the star's core has always produced energy. Atoms give up a little bit of their binding energy each time they are crushed into a stabler, more tightly bound element, and this energy maintains the star's tremendous size. However, Iron is the most tightly bound and stable nuclei there is, and so any attempt to change this element's nuclear structure will require energy from somewhere, instead of releasing it. Thus, any nuclear reactions beyond the fusion of iron will remove energy from the star's core. As the level of iron at the centre builds up, the energy released by fusion plummets, and the star becomes incapable of keeping its enormous layers puffed up. These layers then collapse suddenly and rapidly under gravity's grip, flying towards the core at speeds of around 23% the speed of light. In a matter of seconds, a star dozens of times the diameter of the Sun recedes into a ball of crushed subatomic particles the size of a city. However, these subatomic particles don't want to be crushed together. The free-roaming electrons within the increasingly compressed layers of the star begin exerting a force which pushes back against the collapse. But this alone will not be enough to stop it. Once the core's density exceeds several hundred billion times the density of water, negatively charged electrons begin being crushed into atomic nuclei, where they merge with positively charged protons to create non-charged neutrons. The more electrons are forced into atoms, the less electron pressure there is to counter the collapse, which results in more electrons succumbing to pressure in a snowballing process. Eventually, with the density of the core equivalent to that of an atomic nucleus, atoms are so bursting with neutrons that they begin to spill out and escape, like toothpaste being forced out of a tube. Much like electrons, free-roaming neutrons really don't want to be compressed, and they exert a much stronger repelling force than the electrons, which abruptly halts the collapse of the star when the core is between 12 and 25 kilometers wide. At this point, we have a neutron star. If it is particularly heavy, then it will continue to collapse into a black hole. But either way, the force exerted by the neutrons does manage to stop the collapse of the star at a certain stage. And it is at this point that the chain reaction of a supernova begins. The collapsing layers of the star are abruptly halted, jolting the material and sending a powerful shockwave cascading in the opposite direction. But this alone is not enough to cause the level of explosion we see. There is another, stronger force at work: neutrinos. Neutrinos are a kind of subatomic particle which barely interact with matter and light, and so you can think of them like little ghost particles floating around in the background of space. These tiny units of energy are created every time protons and electrons merge into neutrons, and the power they carry off with them is off the charts, greater than the power of all the stars in a billion galaxies. And, though these neutrinos do not ordinarily interact with matter, under conditions this extreme, with light and matter coupled together, they do interact slightly within the star, depositing a small amount of their energy into the collapsed layers. Even a negligible portion of this total energy is enough to unleash a cosmic nuke, resulting in a massive energy input that reverses the collapse, driving the layers outwards with unbelievable force. The resulting explosion is a Type II supernova, also known as a core collapse supernova, which releases billions of suns worth of energy in a matter of days, freeing the heavy elements fused inside the star's core in the process. Elements vital for life, like oxygen, carbon and iron, and even heavier elements than that. As the explosion ensues, swathes of newly formed neutrons flood through the expanding oceans of atomic nuclei and are captured via the R process, synthesizing elements heavier than iron, like gold and silver, in the star's dying breaths. Type II supernovae can be broken down into a few classes, which are classified based on the behavior of their light curves after the explosion. Exploding stars between 8 and 15 times the mass of our Sun will result in a Type 2P supernova. P for plateau in this case, due to the fact that this kind exhibits a period of sustained slow dimming before dropping off. It is by far the most common class of Type 2, accounting for more than half of all observed core collapse supernovae. Somewhat rarer is the Type 2 linear supernova, where stars greater than 15 times the Sun's mass follow a steady linear decline after their initial peak in luminosity. There's also the Type 2b, which shows a single weak hydrogen emission line, owing to an old star's depleted hydrogen shell. Similarly, there's the Type 2n, N being for narrow in this case.
You will never need to know all these subtypes.
Where thin or intermediate width hydrogen emission lines appear in the star's spectrum. These are thought to be the result of luminous blue variable stars exploding within dense clouds of their own material. Next, we come to Type 1 supernovae. Supernovae which do not show hydrogen in their spectrums. They come in three varieties: the Type 1a, 1b, and 1c. Much like Type 2's, Type 1b and 1c are thought to be the result of core collapse, but with an absence of hydrogen emissions. Therefore, we refer to this kind as stripped core collapse supernovae. Both subgroups are believed to be the result of extremely massive, unstable and eruptive Wolf-Rayet stars, volatile stars with high metallicities, producing strong stellar winds which have blown away their lightest elements. A Type 1b supernova lacks hydrogen in its spectrum, but shows helium, whereas a Type 1c supernova lacks both hydrogen and helium, owing to the fact that it is a Wolf-Rayet star at a more evolved stage, where it has lost more of its light elements. But broadly speaking, these two types occur and proceed in a similar way to the Type 2 supernovae. Of the Type 1s, it is the first and foremost, the Type 1a, where things really start to get interesting. Unlike the other kinds discussed, Type 1a supernovae are not the result of core collapse. Rather, they occur in binary star systems with one or more white dwarf stars. White dwarfs are another way in which stars end their lives. As mentioned, stars less than 8 times our Sun's mass won't end in a supernova. They are not massive enough to work their way up the fusion chain. Instead, fusion will subside around the production of carbon into oxygen, and with no more energy to keep itself held together, rather than exploding, the outer layers of the star will peacefully stream away and disperse into a planetary nebula. What remains of the star is its now exposed core, an Earth-sized sphere of crystallizing carbon and oxygen matter, and thus we have a white dwarf. White dwarfs are, by themselves, incredibly stable. When our Sun evolves into one, it will stay luminous for another quadrillion years or so, before it finally goes out. However, white dwarfs don't always exist in isolation. Many evolve in old binary star systems where they have a massive companion. Then you have the ingredients for a Type 1a supernova. While stable by themselves, all white dwarfs share a deadly hidden property. Above a certain mass, known as the Chandrasekhar limit, a runaway thermal-nuclear process will take hold that causes the white dwarf star to explode, ejecting its superluminous carbon and oxygen matter along with silicon and iron, which appears in its spectrum. Ordinarily, white dwarfs don't usually gain the mass required to reach this level, but with a late-stage stellar companion ejecting material nearby, some of it will inevitably fall onto the white dwarf star and grow its mass. Then, when it reaches this deadly threshold, about 1.4 times the mass of the Sun, the star explodes in what is the brightest supernova there is, so bright that they can outshine an entire galaxy from billions of light years across space. Because Type 1a supernovae always occur at the same critical mass point, they share a common peak luminosity. This makes them a very useful indicator of cosmic distances. If we take something with a known luminosity, we can use it as a marker, known as a standard candle, to work out how far away that marker is by measuring its dimness and redshift. Many projects probed the depths of the universe using this technique throughout the 90s and early 2000s in an attempt to measure its rate of expansion. Previously, scientists had predicted that the universe's expansion would slow down over time due to the gravity of the galaxies within pulling it back. But when we started hunting for distant Type 1a supernovae, we found evidence of the opposite. The most remote Type 1a supernovae seem to be considerably farther away and dimmer than they should be in a universe which is slowing down. Rather, it's as if the universe has expanded more in the recent half of its life, and that its expansion is accelerating. A far cry from previous theories, Type 1a supernovae led to the revelation that the universe is filled with a mysterious anti-gravity force known as dark energy, which is crucial to our current ideas on the behaviour of the large-scale universe. Fritz Zwicky did propose further classes of supernova, the Type 3, Type 4 and Type 5, based on certain individual instances of these explosions which did not fit the agreed characteristics of the first two. However, it is thought that these classes are actually the result of certain imposter nova events which mimic supernova traits. Generally, our Type 1s and our Type 2s are our main classes, understood via the science of nuclear physics and evidenced by observations. But with that said, there is one more kind of stellar explosion that we've yet to discuss. One that is not as bright or long-lasting as a standard supernova, but still constitutes an apocalyptic, yet fruitful explosion nonetheless. A cataclysm caused not by a collapsing star, but by a pair of rotating neutron stars. Two dead, superdense stellar cores left behind by supernovae. If these two extreme objects manage to remain intertwined after their creation, the consequence can be an even wilder kind of explosion. As the neutron stars circle each other, their vice-like counterbalancing influences will cause their orbits to decay. The closer they draw, the faster they will spin, until they are travelling at more than 60% the speed of light, rippling the very fabric of space and sending reverberations across the entire universe in the form of gravitational waves. Once these two neutron stars reach a critical distance, their tidal stresses become so strong that their up until now indestructible iron shells will shatter, exposing both of their interiors. The atomic nucleus density matter on the inside suddenly goes from being around 500 billion times denser than water to no compression whatsoever in the near vacuum of space. This results in a brief but spectacular explosion. One not as bright as a supernova, but one that is detectable from multi-billion light-year distances, thanks to its gravitational wave precursor. This kind of explosion warrants its own class of nova, known as a macronova, and better known as a kilonova. They release enormous quantities of radiation, including their own kind of gamma-ray burst. And like supernovae, they also produce abundances of heavy elements via the R process. Neutrons flood through atomic nuclei in the matter undercaptured, resulting in the production of gold, silver, europium, and strontium, among other elements. This type of explosion is so fruitful, in fact, that some propose colliding neutron stars to be the real source of the universe's heavy elements, but it is not known whether such explosions are common enough in space for this to be true. Nevertheless, supernovae and macronovae explosions are the only way we know of in which materials like gold and silver can be created. So, next time you buy some jewelry,
Okay, really quick. Type 2 supernova. One of the things they were saying characteristically is you look at the spectrum and you're going to see hydrogen. That's because there will still, as that star is going through and it's fusing things, there will still be hydrogen in those outer shells. And as it explodes, you'll see it. But when you get a type 1 supernova, that came from a white dwarf. Well, that white dwarf had already gone through everything and it had shed its outer layers. All that was left is essentially a carbon-oxygen core. There was no hydrogen. Now, it accreted some material from a companion star and then went supernova, but you don't see that characteristic hydrogen line. It's one thing I just do want to say about this. So the type 1s, okay? Right, what you always have here is you have a white dwarf, and it's in a binary system with a giant or supergiant. And so what you see here is, if I were to kind of draw what it looks like, you got a little white dwarf here and you've got a supergiant. Well, this thing, as it's going through its process, its layers are getting further and further away from it. They're less gravitationally bound to that parent star. And now the gravity of this is sufficient to begin attracting some of its material. Okay? So it will literally just get drawn off of this, like getting sucked into a vacuum. Well, as it does, this gets bigger, more dense, more mass. Eventually, it passes what's called the Chandrasekhar limit, which is 1.39 solar mass units. There's no fusion happening here. It's just getting hotter and hotter because there's more and more gravity compressing. Once it reaches that limit of 1.39 solar mass units, it explodes. Always. And it always explodes at exactly that number. Okay? So if you get a white dwarf near a companion star, as it's pulling this off, once it hits that, it always explodes. That's why they were saying this is a standard. We know these always explode at the exact same brightness because they're always exploding at the exact same mass because there is a universal limit to how big a white dwarf can be before it explodes. Okay, that makes sense? Okay. Supergiant stars can fuse elements up to iron. We'll talk about this more coming up, but basically what they're saying is as elements fuse, hydrogen to helium, helium into carbon and bigger stuff, they release energy. But when you fuse iron, iron actually absorbs energy. Which means instead of releasing energy so that the star can continue down its giant phase, it's like which is like continuing to pour gasoline on it as it goes. It's like you just use a fire extinguisher. All of a sudden the fire goes out because it's taking all the energy away. At that point, no more pressure from fusion. All there is gravity. And so once you begin forming iron, that's it, man. That's the end. And it rapidly, I mean, like they're saying like in a second, right? This thing just collapses. And then, that's where this stuff goes. So the core collapses with such force from the gravity that electrons traveling around protons can't stay in their orbitals anymore because of the gravity. They're sucked into the protons, which turns them into neutrons. And then the neutrons exert a certain amount of force, which can prevent the star from collapsing further, in which case you have a neutron star, but if it's massive enough, the contraction continues still, and then you're going to have a type 2 supernova. And in that type 2 supernova, there's enough energy released, and there's the material present from all those neutrons, that it will fuse things heavier than iron. So anything up to iron can be formed in a star. Anything heavier than iron has to be formed in a supernova. Gold, silver, stuff like that. That's why you'll hear so much in astronomy, like the idea that we are stardust, that this is how God made all these elements, is this kind of thing. At least that's what we see in the rest of creation. All right, we'll stop there for today. Next time we'll review some of this, and we'll probably dig in more into the specific stars, and we didn't even talk about black holes yet, so all the funky stuff in space is coming up.